Okay, hi everyone, welcome back. So in this video, we will be looking at the 2012 A-Level H2 Math, Paper 1, question 11. This is the last question of the Paper 1. It is on parametric equations, a little bit on differentiation, and a little bit on application of integration. So this is a cross-topic chapters, cross-topic questions, okay? So for part 1, we're supposed to show that dy dx equals to cotangent half theta. Okay, so for parametric equation, to find dy dx, first of all, you need dx d theta as well as dy d theta. So that's going to be the first thing we do. Differentiate the first equation with respect to theta. You have 1 minus cosine theta. Differentiate the second equation with respect to theta. You will have sine theta. Your dy dx will be dy d theta over dx d theta. But take note, the equation that we are supposed to prove, the angle is half theta. So what we need to do from this step onwards is to use double angle formula to get theta over 2 out. So sine theta is 2 sine A cos A. And then after that, cosine 2A is 1 minus 2 sine square theta over 2. Alright, so some of you might be wondering, how come cosine 2a, there are 3 different equations that we can transform it into, namely cosine square minus sine square, or even 2 cosine square minus 1. How come I choose 1 minus 2 sine square instead? So it all boils down to what we want to prove. I want to prove cotangent half theta. So you need to have this foresight to say that, at the end of the day, I need cotangent half theta, which is equivalent to cosine half theta over sine half theta. That is why I try to have a sine theta over 2 in my denominator. Okay, so that is the chain of thought. That is why I change cosine theta into 1 minus 2 sine square theta over 2, because I need the sine function in the denominator in order to get cotangent. All right. So after that, simplifying, I have 2 sine theta over 2 cosine theta over 2 over 2 sine square theta over 2. So a lot of things will cancel. 2 will cancel. Sine theta over 2 will cancel. So I'm left with cosine theta over 2 over sine theta over 2, which gives me my cotangent half theta. All right, sure. After finding dy dx, we need to find the gradient of the curve at the point where theta is pi. So when theta is pi, dy dx equals to cotangent half theta, which is equivalent to cosine theta over 2 over sine theta over 2. Some of you might be wondering, how come I'm converting dy dx back into cosine theta over 2 over sine theta over 2? It is because your scientific calculator cannot press cotangent. There is no cotangent function. All right, so no choice, you have to convert back. This will give you 0 over 1, which is just 0. So we are done with the gradient of C at the point theta equals to pi. Okay. Okay. Let's look at the second part of part 1. What can be said about the tangent to C as theta tends to 0? and theta tends to 2 pi. So let's look at them one by one. As theta tends to 0, the numerator cosine theta over 2 tends to 1. All right, your sine theta over 2 denominator tends to 0. So your dy dx, you can think of it casually as 1 over 0. It tends to infinity because anything divided by 0 will be undefined. All right, as theta tends to 2 pi, the numerator tends to -1. Your denominator, same thing, tends to 0. So by the same logic, when you are dividing by 0, your dy dx tends to infinity. But this time around, -1 divided by 0, so you have negative infinity. So what can be said about the tangent? The tangent to C as theta tends to 0 and theta tends to 2 pi are parallel to the y-axis. In other words, graphically, the tangents, they are vertical lines. That is why their gradient is undefined, is infinity. Okay. So you guys can pause the video, take down the working, because I'm going to erase them and move on to part 2. For part 2, sketch the curve C, showing clearly the features of the curve at the points where theta is 0, pi, and 2 pi. Okay. So for those of you who cannot draw the shape of this curve, you can use the GC to help you. So let me show you some of the screenshot. This is a parametric equation, so make sure you go to the parametric mode, and then after that, you key in both the x and y equation in terms of t. In the question, it was theta, but then because the GC gives you t, I mean, it's the same thing. After that, before you rush off to see how the graph looks like, a very important step that a lot of students miss out. Make sure you adjust your t settings. Okay, t in the GC is the theta in the question. So it ranges between 0 and 2 pi. Make sure you change the setting first before you look at how the graph looks like. Because for those of you who use 0 and pi over 2, for example, you only see a fraction of the graph, which is not the whole thing. All right, so you have to be careful about that. If you use the correct t values, you should have the whole graph. Right, the graph looks like this. So let's go back to the question and sketch them. So we have the x and the y-axis. We have an oval shape looking thing. Now, if you want to find the points where theta is 0, pi, and 2 pi, you have to solve them manually. So for example, when theta is 0, x is 0, y is 0. So we have this point of origin. And then when theta is pi, x is pi minus sine pi. Sine pi is 0, so x is just pi. Y equals to 1 minus cosine pi is -1. So we have 2. This point over here, pi 2. And then when theta is 2 pi, x is equals to 2 pi minus sine 2 pi. Sine 2 pi is 0. y is 1 minus cosine 2 pi, which is 1. So you get 0. This is the third point. So this is 2 pi, 0. Okay. Moving on to part 3. Without using a calculator, find the exact area of the region bounded by C and the x-axis. So basically, we are talking about this region, okay, the curve and the x-axis. So area, we integrate with respect to the x-axis from 0 all the way to 2 pi, because this point here is 2 pi. So 0 all the way to 2 pi. Why? Dx, because we are integrating with respect to the x-axis. You have to do a change of variable, okay? So let me show you some side working. When x equals to 0, if you do the calculation, theta equals to 0. So use these two equations to do your calculation. When x is 2 pi, theta equals to 2 pi. So it just so happened that, in this case, when x is 0, theta is 0. When x is 2 pi, theta is 2 pi. But they are not always the same. So make sure you check, okay, when you are doing changing of variable. Okay, then y equals to 1 minus cosine theta. Okay, no problem. Change the y to 1 minus cosine theta. So up until this point, I have changed the lower and upper limit from x to theta. I have changed y to become 1 minus cosine theta based on the equation. The last thing I need to change is dx. So from part 1, if you go back to the part 1's working, you can get dx equals to 1 minus cosine theta d theta. This is from part 1. So simplifying, if you open up the bracket, you have 1 minus 2 cosine theta plus cosine square theta d theta. So you can change the trigo identity. For 1 and minus 2 cosine theta, I'm not going to change anything because it's easy to integrate already. The only thing that I'm going to change is the cosine square theta. I'm going to change it to 1 plus cosine 2 theta over 2. So that it's easier for me to integrate. Okay, so let's perform the integration. Integrate 1, you get theta. Integrate 2 cosine theta, you get negative 2 sine theta. Then after that, integrate 1, you get theta. Integrate cosine 2 theta, you get sine 2 theta over 2, which is half sine 2 theta. Upper endpoint, lower endpoint. So next step, you plug in the upper and lower endpoint. You get 2 pi plus half 2 pi. A lot of things becomes 0. So while it looks very complicated at the start, right? After you sub in the 2 pi value and the 0 value inside, you realize a lot of things actually disappear because they become 0. So all in all, area under the graph, 3 pi units squared. You can pause the video right now to take down the working. I'm going to erase them and move on to part 4. A point P on C has parameter small p, where p is between 0 and pi over 2. Show that the normal to C at P crosses the x-axis at the following point. Okay. So first of all, the P coordinate looks something like this. Okay, replace the theta with small p. Then after that, dy dx at P, big P, this is big P, at point P equals to cotangent small p over 2, which is sine P over 1 minus cosine P. I'm based on the working in part 1. Okay, so I repeat, you get this from part 1. Okay, then gradient of normal at P equals to, so you reciprocate it and you change the sign. This will give you cosine P minus 1 over sine P. Okay, so for those of you who cannot follow what I'm doing, basically I'm using this. M1 times M2, if they are gradient of two perpendicular lines, equals to -1. This is the formula that a lot of teachers teach the students to use. But for me, a shortcut to this will be you simply reciprocate the dy dx and you add a negative sign to it. That will give you the gradient of the normal. It's a faster way. Okay, so equation of normal at P is given by y minus y1 equals to m, the gradient, x minus x1. When the curve crosses the x-axis, y equals to 0. So when y equals to 0, -1 plus cosine p equals to cosine p minus 1 over sine p. So I'm not doing anything much from the previous step to this step. I am merely changing y to 0. Okay. Then the next step, we can open up the bracket. Okay, so I'm going to multiply this into the bracket. Plus k plus p minus p cosine p over sine p plus cosine p minus 1. Okay. And then after that, all the terms with x, we put it on the left-hand side. And then all the terms with no x, we put it on the other side. So we have p cosine p minus 1 over sine p. Okay, so it seems that it's very abrupt for us to jump from one step to the other, but actually it's nothing much. This -1 cancel with the -1, cosine p cancel with the cosine p. I am basically shifting this term over to the other side. That's all. Okay. So some of you might get confused. Hey, how come the p minus p cosine p changes position? It's because we multiply by -1. Okay, so you can don't write the negative sign by changing the position of the terms. You realize that, this coefficient of x is actually the same as the second term on the right-hand side. In other words, we can cancel them off, and x is simply p. Okay, so we have shown that the normal passes through P0. Shown. Okay, so that's all for question 11, the last question of paper 1. I see you guys in the next video for the first question in paper 2. All right, see you guys in the next video.